Welcome to my presentation on LRPD, Long-Range Pedestrian Detection leveraging specific strengths of LiDAR and RGB. My name is Michael Fürst and I'm from DFKI, and in the remainder of this presentation I will present you our approach. Vulnerable road user detection is a major challenge to be solved for autonomous vehicles. The vehicle should avoid all objects, including pedestrians. One key challenge is detection pedestrians at long range. For vehicles in urban areas, a typical braking distance is between 20 and 50 meters, assuming a braking acceleration of 0.5 g, leading to a trustworthy, safe and comfortable driving function. Beyond comfort range, long-range pedestrian detection plays a huge role in safety for autonomous vehicles, as the distance gives the vehicle extra time for tracking and decision-making, which is critical. The image you can see is seen from the KITTI dataset containing pedestrians at almost all ranges. The bird's eye view representation at the bottom is colored. The first zone is the zone from 0 to 10 meters, colored in red. The second zone is the zone from 10 to 20 meters, colored in amber, and those are the pedestrians you can see in the foreground of the image. The next zone is the zone from 20 to 30 meters in yellow, where we have very few pedestrians, and the last zone is the 30 meter plus zone. And those pedestrians on the far left side are the pedestrians that need to be detected for a safe and smooth driving experience. For analysis, we use the KITTI benchmark, as it is the default benchmark for all 3D object detection tasks. It has almost all state-of-the-art approaches evaluated on it, and that is why we also do our quantitative analysis on the KITTI dataset. On the other hand, the new scenes dataset has fewer approaches tested, and those approaches are mainly LiDAR-only approaches. But it has day, rain and night, and we will see in our evaluation later that rain is an interesting condition where our approach also succeeds. So we compared the state of the art and categorized it into 3 strategies to the detection problem. The first strategy is LiDAR only, where point pillars is the main representative of this category. It first has a LiDAR encoder, then a bird eye view backbone, and finally applies a 3D detection head. TANet is a descendant of Point RCN and VoxelNet are 2 other approaches in this category. The next category is first RGB, then LiDAR, the main representative for us being FPointNet, which has first an RGB encoder, then it uses an RPN to predict 2D bounding boxes. Those bounding boxes are extended into a frustum and crop the LiDAR point cloud, which then is fed through a PointNet into a 3D detection head. The 2 other approaches in this category, FConfNet and iPod, were slightly different, but share the core idea of first using RGB to get region proposals or proposals, and then using LiDAR only for the refinement. Last category is symmetrical fusion. We have AVOD as a main representative and the extension VMVS. And it works by essentially having 2 encoders for RGB and LiDAR, which are in parallel. They are fused in an RPN and then after that concatenate. The 3D detection head is again here in the end. Our approach, LRPD, fits into 2 of those categories, into first RGB and then LiDAR, and the symmetrical fusion heavily are inspired by both those approaches and take the best of both worlds. And what we wanted to do with those categories is we wanted to analyze what impact do they have on performance, and we found some impact, especially for the long range, which we can see on the right hand side. We have point pillars with a very strong decrease in performance on long range, 30 plus meters, FPointNet with also a strong decrease, and AVOD with a little less decrease but also a strong loss in. And what we can see here is that the more the approach depends on LiDAR, the less accuracy for long range is. And AVOD, which has a symmetrical fusion, has the best results of the 3 categories. And we wanted to know why that is the case, and for that we analyzed those long range cases, and we found that on average they have 706 pixels in the area of the and 18 LiDAR points. But we found also that hard examples have only 1 to 7 LiDAR points, which is very few and makes it impossible from only LiDAR points to detect that this is a person. And this leads us to the conclusion that the dependency on LiDAR in current state of for the recognition of pedestrians is very unsuited for the task. And this means that LiDAR only and RGB then LiDAR approach, which heavily rely on are not suited for long-range pedestrian detection. The best so far is symmetrical fusion, but as we will see, all strategies are suboptimal for long range and there is some more refinement required. This is why we introduce our design principle for the long-range pedestrian detection, and our design principle is RGB for recognition robustness and LiDAR for localization precision. Whereas in RGB we have a lot of pixels with which we can classify if the thing we're looking at is a pedestrian or not, and in the LiDAR we have centimeter precision for the localization of the object. The overview of our approach can be seen here. It can be separated into 3 parts. The first part is the proposal generation, the second part feature extraction, and the third part is refinement. And we can see the inputs to our approach are an image and the bird's eye view representation of the scenery. The proposal generation starts by first having an instance segmentation. In our case we use mask RCNN. After that we have a point cloud masking where we apply those instance masks on the point cloud and get the points for each instance. Then for every point per instance we create an anchor, which leads us with a lot of anchors. In the case of a hard example where we have on average 19 LiDAR points for this example, we will have on average 19 proposals, which is too many proposals. For that we do non-maximum suppression, where we use the number of inlier points for the box. So the box which best fits all LiDAR points from the point cloud segmentation is the box which survives the non-maximum suppression. And finally we do some proposal augmentation during training to increase our accuracy more. An advantage of this strategy for the fusion is that if we have the assumption that one inlier point is existent for a pedestrian, then we can get pedestrian has a instance segmentation has one inlier point. And this is a very strong thing, especially with occlusion. When we have 2 pedestrians which are close to each other, then we know the proposal for each pedestrian, and we know that the proposals will not accidentally get merged between the 2, which will happen if you use semantic segmentation. The next is our feature extraction stage. The feature extraction has first ROI crops on the 2 image streams, so the image stream and the bird's eye view stream, and then it applies the feature extractors. After the feature extractors, global average pooling is done and the features are concatenated of the 2 streams. With those features, they are fed in the refinement through a fully connected layer and then directly into the heads of our network. We have 4 heads. One head is for object, one head is for position, one head is for size, and one head is for orientation. For position and size, we only regress the deltas to the anchor. We use as a loss for the objectness the automated focal loss, for position, size, and orientation a smooth L1 loss. And for orientation, it is worth mentioning that we use the sine-cosine representation. As has been shown by other papers, the representation as the angle has disadvantages with the jump from 0 to 360 or at minus 180, 180. Finally, we want to show our results on the KITTI dataset, the KITTI mean average precision in bird's eye view. And we have this table with all the results from the top approaches: AVOD, point pillars, f.net, iPod, point RCNN. And what we can see is that our approach is comparable to in its performance to the other approaches on the regular KITTI metric demarked as all. All means that it is evaluated on all ranges. We can see, however, if we look at the columns demarked with LR for long range, that in the long range case our approach always outperforms all the other approaches. We can see for moderate precision of 15.6 compared to the second best with 12.6. In the easy case we have 38 compared to the best approach with 26.1. And in the case of hard we are having 15.7 compared to the best with 12.1. And in the hard case we even outperform over all distances. This is due to the way KITTI classifies hard. Hard has a bias towards long range, giving us an edge. On the right hand side in this diagram, we can see a detailed distance analysis of our approach. And here we can see what it actually means that our approach is strong in long range. If we look at the range, we can see that our approach from 20 to 30 meters and 30 plus meters has no decrease in accuracy in contrast to all other approaches, point pillars, f.net, AVOD. And that is the strength of our fusion scheme. Next, we did some additional metrics, and here we can see that with the F1 score, precision and recall, our approach is far superior to all other approaches. However, in the 3D Euclidean error, it has a less precision. And this was a decision in our process of the approach, as strong recognition is more important for the safety of a vehicle and the smooth driving experience than the precise localization. Therefore, LRPD has a strong recognition and suboptimal localization by design. In our results, we also did an ablation study. In this ablation study, you can see that change of the encoder has minor effects on the results or secondary effects on the results. However, the most significant changes in the result are coming from changing the refinement modalities. So RGB and LiDAR has the best results, whereas LiDAR only has significant drop in performance, and RGB only almost cripples our approach. For augmentation scheme, we can see that the augmentation scheme also has a huge impact on the performance of our algorithm, with the random augmentation giving it a huge edge on performance and combining random augmentation with grounding yielding best results. So overall, the most contribution to the precision of our approach comes from RGB LiDAR fusion and proposal generation, whereas the encoder only plays a secondary role. In this qualitative analysis, we have results from AVOD, F.net, point pillars, and LRPD, and from left to right we have different scenarios. In the leftmost scenario, we can see two pedestrians at the far side of the crossing, and we can see that AVOD only detects one pedestrian, F.net detects both but has a false positive on the center island. Point pillars cannot detect any of the two pedestrians, and our approach reliably detects the two pedestrians without false positives. In the center row, we can see a cyclist, and that cyclist is a false positive in the case of AVOD and our. This is a common failure case for the approaches that they detect cyclists as pedestrians. On the right-hand side, we can see where AVOD struggles with detecting all the faraway pedestrians. F.net is capable of detecting the faraway pedestrians, but only threshold so that we have a lot of false positives in the foreground. Point pillars has no chance of detecting the pedestrians in the far range, and our approach can detect the pedestrians at the far range without sacrificing close range and not having false positives here. In this next image from new scenes, we can see a surround view of new scenes, and we have the instance masks network in red and the final predictions in cyan. We can see on the left bottom that there is instance mask predictions inside of the car, which are false positives, but our second stage of the network, using the LiDAR, successfully figures out that those are not pedestrian and only marks the pedestrians which are actually in the scene as pedestrians. Finally, I want to show two videos. One is a video during business and one is. In this video, you can see pedestrians in the crowd, and on the right-hand side now, you can see a crowd of pedestrians which is far away, which is reliably detected. We can also see here on the left, there is two pedestrians, and as we will get closer, we will still be able to see them. And also here in the very far right, we can also detect this pedestrian. The next is during night, and here I want you to focus on the bus, because on the right hand side there will be a person appearing behind the bus, which despite all the water drops on the sensor, our approach is able to reliably detect. So here we see the person on the right hand side despite the rain, and on the left we can see all the bicycles which have been detected by the approach as bicycle. And here we can see that the pedestrian, despite being far away in the rear of our vehicle, can still be detected reliably. So in conclusion, our approach, we found that the poor long-range performance of existing approaches is due to the few LiDAR points which exist and the lack of adaptation to that. State-of-the-art currently highly depends on LiDAR for the recognition of pedestrians, but we think that for recognition of pedestrians, you should use RGB and robustness, and we did that in our approach, and we used LiDAR for the localization precision in the second stage. This gives us competitive results on KITTI and a substantial improvement on long range. Thank you for your attention. On the right-hand side, you can find all our contact informations.